One of the common types of solids we're going to be looking at in this class is solids of revolution. And these are basically formed when you have a curve, or more often a region in the plane, and you rotate it around an axis. So here is an example where we're going to find the volume of a solid inside this surface that is formed by revolving the curve y equals 1 over x from x equals 1 to x equals 3 around the x-axis. So I have a picture of this, and here's the curve y equals 1 over x, and it is highlighted the part of the curve where x goes from 1 to 3. And I'm going to take that curve and kind of move it outside of the plane and revolve it around the x-axis. So what that's going to look like here is, so it's going to come down to this side, and it's going to revolve around the x-axis like this. So if I was to take slices at each x value between 1 and 3, then those slices would look like circles. So I'm going to draw a representative slice. Here's an x value, and I will have this circle, this disk, and that's going to be my slice at an x value. Okay, if I look at that, the radius of that circle is going to be, the y value. So the area is going to be pi times y squared. But this comes from y equals 1 over x. So that area is going to be pi times 1 over x squared. Then the integral, or the volume, is going to be the integral from 1 to 3. Those are the x values for this particular integration of a of x dx, which is pi times 1 over x squared dx. This is pi times, this is antiderivative of x to the minus 2 would be negative 1 over x, evaluated from 1 to 3, which is pi times negative 1/3 minus a negative 1, which is going to be 2/3 pi. So the volume then is going to be 2/3 pi, and I'm just going to re-emphasize this. It's cubic units, whatever the units are, whatever the length units are. It's those units cubed. I did put here a picture of that solid so that you can kind of see it in a little bit more glory than the way that I could draw it. One of the skills that you will be developing in Calc 2 is both imagining and drawing some solids of revolution, or solids of different shapes. And I think it's helpful to have some visualizations to kind of give you something to ground on and give you some ideas about what to imagine. All right, let's take another example. We're going to take the same curve, and instead of revolving it around the x-axis, we're going to revolve it around the y-axis. So it's the same portion of curve that's right here. Okay, and I'm going to revolve it around the y-axis. So it's going to end up coming over here like this, and it's going to look like a hat or something, except it's going to be solid, so you wouldn't be able to fit your head in it. Okay, or a lampshade. Now, in this case, I don't want to take slices in the x direction. If I take slices in the x direction, then I would have, these sort of awkward looking slices that look like that. So that's not what I want to do. I instead am going to take slices in the y direction. And so for any given y value, I'm going to have a circular slice like this. So that's a y value. And again, the area is going to be pi r squared, but in this case, the r here is the x coordinate. Okay, so this is going to be pi times the x coordinate squared. But since I'm taking a slice at each y value, I'm going to be integrating with respect to y, so I need to write this in terms of y. This curve is y equals 1 over x, so we need to solve that for x, and that is basically x equals 1 over y. Reciprocal function is its own inverse. So the area as a function of y is going to be pi times 1 over y squared. So that means the volume is going to be an integral of pi times 1 over y squared dy. And remember, this goes from x equals 1 to x equals 3, which means it's going to go from y equals, so x equals 1 is going to be y equals 1 as well. And x equals 3 is going to be y equals 1/3. So the lower bound is going to be 1/3 and the upper bound is going to be 1. So I am integrating from 1/3 to 1. Shift this over a little bit, give myself room to work. So this volume is going to be pi times negative 1 over y, evaluated from 1/3 to 1. So this is pi times negative 1 minus negative 1 over 1/3, which is pi times negative 1 plus 3, which is 2 pi. So in this case, the volume is 2 pi cubic units. Okay, again, I got a picture of this so that you can see a more beautifully rendered picture. So that would be roughly what this surface looks like. And you can kind of, it's a little bit translucent. You can see the region of the surface that is actually rotated about the y-axis. All right, I think we have 2 more examples here. Here we have, find the volume of the solid formed by rotating the region bounded by y equals x squared minus 2x plus 2 and y equals 2x minus 1 about the x-axis. So in this case, instead of saying I'm just rotating a curve and saying, whatever is inside the surface that you get from rotating that curve around an axis, here I'm taking a region and I'm rotating it around. And you can kind of, it's not different. So when I said like the solid that's inside the surface formed by rotating this curve, you can see in this computer rendering what they did is it actually ended up rotating this region. The region between the curve and the x-axis got rotated around the axis, and that created a solid. Similarly, in example 5, the region was the region between the curve and the y-axis got rotated around the y-axis, and that created a solid. Okay, so here we're going to take this region. The parabola here is given by y equals x squared minus 2x plus 2, and the red curve is given by y equals 2x minus 1. We're going to take that region and we're going to rotate it around the x-axis. So I can visualize that. I'm going to do something like this and something like this. And so when I rotate that around the x-axis, I'm going to get this thing that looks like this. And this is actually going to be kind of a similar looking lampshade or hat thing, except it's going to be, it's going to have space inside it. Okay, so there's this empty hole inside. I will actually show you the picture of what this looks like before I do anything further. Okay, so that's one perspective of it. And so you can see a little bit the sliver of, this is the region here that was rotated around the axis. So when I do this, if I choose some, I'm going to integrate with respect to x. And when I choose some random x value, what that's going to do is it's going to have, basically there's this line segment that fits in that region, and that line segment is going to be rotated around, and it is going to create a hollow disk, often referred to as a washer. So I am going to draw this in, it's going to be something like this. Okay, it's like a circle with a circle removed from the center. Okay, so this is often referred to as a washer shape. And then if we think about this, there's two radii here. There's a bigger radius, which I'll label big R, and an inner radius, which I'll label little r. And the area of this is going to be pi times the big radius squared minus pi times the little radius squared. So it's essentially the area of the big circle minus the area of the small circle. Okay, so now we just need to think about what are those two radii? And both of those radii are y values. So the bigger radius is the y value coming from the linear curve. So I would write the big radius is the y value coming from the linear curve, which is 2x minus 1. And the little radius is the y value from the quadratic curve, which is x squared minus 2x plus 2. I need to figure out what the intersection points are. This is essentially solving x squared plus minus 2x plus 2 should equal 2x minus 1. Let's see, subtract 2x and add 1 to both sides. So I have x squared minus 4x plus 3 equals 0. That factors as x minus 1 times x minus 3 equals 0. So that says x equals 1 or x equals 3. That seems consistent with the graph. These seem to intersect here at x equals 1 and here at x equals 3. Let's double check. At x equals 1, we have the linear curve is 2 times 1 minus 1 is 1, and the quadratic curve is 1 squared minus 2 times 1 plus 2 is 1 minus 2 plus 2, which is 1. Okay, same y value. So the intersection point of the two curves is 1, 1. This matches what we're seeing on the graph. At x equals 3, the linear curve is 2 times 3 minus 1, which is 6 minus 1 is 5. And the quadratic is 3 squared minus 2 times 3 plus 1. This is 9 minus 6 plus 1. Doesn't seem right. 9 minus 6 is 3. Nope, that is not plus 1. It's supposed to be plus 2. Plus 2, which is 5. So both of these have a y value of 5 at x equals 3. So we have an intersection point at 3, 5. Now we can actually calculate the area. So we're going to integrate pi times the big R squared, so 2x minus 1 all squared, minus pi times the little r squared, so x squared minus 2x plus 2 all squared, all of this times dx. Again, let's just, since we've done a few of these, remind ourselves what this is. This is basically the volume of a thin washer, which is the area of that washer times the thickness of the washer, which is dx. It comes from delta x. Okay. We're integrating this for different x values, and the x values are going to range from 1 to 3 based on those intersection points that we found. Okay, so I'm going to pull that pi constant out, and I need to simplify these polynomials. I'm going to square the 2x squared minus 1, that's 4x squared minus 4x plus 1. And I'm going to square the x squared minus 2x plus 2. I did this previously, so I'm going to copy the work that I did. So that is x to the 4th minus 4x to the 3rd plus 8x squared minus 8x plus 4 dx. Volume equals integral from 1 to 3. And simplify this a little bit more. Integral of minus x to the 4th plus 4x cubed minus 4x squared plus 4x minus 3 dx. And I differentiate this. This is integrating from 1 to 3. Pi times minus 1/5 x to the 5th plus x to the 4th minus 4/3 x to the 3rd plus 2x squared minus 3x evaluated from 1 to 3. I am not going to do that on video, so this ends up being 104/15 pi, which is approximately 21.8 cubic units. All right, one last one. We're going to take this same region, and instead of rotating around the x-axis, I'm going to rotate it around the line x equals 4. So that line is here. I'm going to put that up. So that's x equals 4. And so what we're going to do is we're going to take that and we're going to rotate it around that line. And I get this sort of different lampshade looking thing. It's going to be hollow, but it's going to have some thickness in the lampshade part. This time I'm going to integrate with respect to y because I want, again, I want to think about what kind of slices I get. If I integrate with respect to x, I'm going to have some weird looking slices. So I want to integrate with respect to y. And if I pick some y value and look at what sort of shape I'm going to get a washer here. I want to look on this side. This is where my curve is defined. So my big R is going to be 4 minus the x from the linear function. Let me say this. How about big R is going to be 4 minus the x from the linear function, and the smaller r is going to be 4 minus x from the quadratic function. This is going to be harder, okay? That means we've got to actually solve for x in both of those, and that's fine in the linear function. It's harder in the quadratic, but we can do it. Okay, so for the linear function, it is y equals 2x minus 1. So y plus 1 equals 2x. So x equals 1/2 of y plus 1. For the quadratic, we have y equals, what is it? X squared minus 2x plus 2. I think probably a good way to do this is to actually complete the square, and I'm actually going to use the graph to help me. I can see that the vertex is at 1, 1, and so I'm going to look at this and see this is y equals x squared minus 2x. That 2 I can write as plus 1, and this x squared minus 2x plus 1 is the same as x minus 1 all squared. Okay, this one I can solve for x, so y minus 1 equals x minus 1 all squared. So x minus 1 should be equal to plus or minus the square root of y minus 1. And so there are 2 halves to this curve, and that basically boils down to there's the right half or the left half. And the right half is going to be the positive side. So we're going to use the positive square root here. And so we have x is equal to 1 plus the square root of y minus 1. It is not pretty. And it turns out this one is a little bit better suited to do with cylindrical shells rather than with washers. But I wanted to do this to kind of show you what this process looks like and show you all of the parts that go along with this. So let's take this up here. The volume is going to be an integral. It's going to be pi times the big R squared minus pi times the little r squared. That's how we calculate the area of one of these washer shapes. Times dx, times dy, that gives me the volume. And in the previous example, we actually calculated the y values of this. Those 2 intersection points are at 1, 1 and 3, 5. Okay, so we didn't necessarily need to calculate the y coordinates. I was verifying that these were actually the correct intersection points for those 2 curves, but it's nice that we got that. So in here we have the y coordinate goes from 1 to 5. So I'm integrating from 1 to 5 of that. So this is an integral from 1 to 5. I'm going to pull that pi out. And the big R is 4 minus x time from the linear. So there's going to be a lot going on here. So the big R is 4 minus the x from the linear is 1/2 of y plus 1. That big R is squared. And then we subtract off pi times little r squared. So the little r is going to be 4 minus the x from the quadratic. So it's 1 plus the square root of y minus 1. 1 plus the square root of y minus 1. That is all squared. dy. So let's do this. This is the same thing as pi times the integral from 1 to 5. I'm going to simplify what's in here before I square it. So this is going to be negative 1/2 y. And we're going to have plus 4 and minus 1/2 is going to be plus 7 halves. That's all squared. Minus, we have 4 minus 1 is 3, and then we have minus the square root of y minus 1. That's what's inside the parentheses. We square that, dy. So for this, I'm actually going to take that 1/2 out of it here so that I can more easily square this. So that's going to be a 1/4 when I square it. So pi integral from 1 to 5, there's going to be 1/4 times, and I'm actually going to take out a minus 1/2. So I'm squaring y minus 7. And this one, when I square it, it's going to be 9 minus 6 times the square root of y minus 1 plus the square of that, which is y minus 1. Okay, all of this times dy. Fun algebra skills. I'm going to move this stuff out of the way. So this is pi times the integral from 1 to 5 of 1/4 times y squared minus 14y plus 49 minus the quantity. Let's see, there's a y, plus 9 and minus 1 would be plus 8, and minus 6 root y minus 1, all of this times dy. Okay, so this is pi times the integral from 1 to 5. Oh, let's see, we have 1/4 y squared. This is going to be minus 7/2 y, minus 7/2, and minus another 1y would be minus 9/2 y. And this would be plus 49/4. So 49/4, and we have minus 8 is 32/4. So that would be plus 17/4. And then we have plus 6 times the square root of y minus 1. Super fun. Okay, we can anti-differentiate this using basically the power rule. This is a power function of y minus 1, so we could do a u substitution for that, where u equals y minus 1, and then du would be just dy. I'm going to skip to the end, just the result of that. So this is pi times, so 1/3 y cubed, so that would be 1/12 y cubed. This would be minus 9/4 y squared plus 17/4 y plus 6 times, this is y minus 1 to the 1/2, so it would be y minus 1 to the 3/2 power, and we would multiply that by 2/3. This is all evaluated from 1 to 5. So this is going to be pi times, I'm going to evaluate each piece from 1 to 5. So this is 1/12 of 5 cubed is 125, and minus 1 cubed is 1, minus 9/4 times 25 minus 1, plus 17/4 times 5 minus 1. That 6 times 2/3 is plus 4, times 4 to the 3/2 minus 0 to the 3/2. Pi times, that's 124/12 minus, that's 24 divided by 4 is 6, so 9 times 6 is 54. 17/4 times 4 is plus 17, plus 4 times 4 to the 3 halves. Well, that's the square root of 4 cubed, which is 8. 1/24 is, let's see, there's a 4 that fits in both of those. So 31 thirds. And this looks like 32 plus 17 is 49. So plus 49 and minus 54 looks like minus 5. So that is minus 15 thirds. Looks like 16 thirds pi. I am going to actually check this. Okay, I'm going to go to Wolfram Alpha, and I'm going to integrate. I'm going to go to the original integral, which is going to be pi times, I want 2 parentheses, 4 minus 1/2 of y plus 1 squared minus 4 minus 1 plus the square root of y minus 1 squared. I can actually take that parentheses out and put dy. Let's double check to make sure that it's got the same thing. So this is 4 minus 1/2 y plus 1 squared minus 4 minus 1 plus square root of 1 y minus 1 squared dy. Oh, for y equals 1 to 5. So we got 16 pi over 3, which is exactly what we got in calculations. Okay. So this was not pretty. And part of what was not pretty about it was that this was 2 functions that were given very simply as y as functions of x, and we had to convert them to functions in y in order to use the disk method. In the next section, we'll learn about the washer method, which will allow us to do this same, calculate the same volume, but with a more simplified integral.